today I'm going to talk about research I started as a Blue Waters Fellow that I've carried on into this past year, looking at how cosmic ray-driven outflows shape the circumgalactic medium. So I'm going to start out by talking, giving a brief introduction about the CGM and why it matters. So loosely defined, the CGM is the diffuse gas that extends from the galactic disk all the way out to the dark matter, or the edge of the dark matter halo in which a galaxy lies. So what we're used to thinking of a galaxy is this little thing right here, and everything else is the circumgalactic medium, or the CGM. And so you'll notice that it has a really rich structure, which is something that observations have only recently discovered in the last 5 or so years, because this gas is so diffuse that it's nearly impossible to observe directly in emission, and so we've had to go to space in order to be able to study the CGM of different galaxies in absorption. And some of the key highlights that we now know about the CGM is that, one, the CGM holds the majority of all baryons, which means everything that's normal matter, that's non-dark matter or dark energy, and on top of that, it holds the majority of all metals, which is really interesting because metals, and I should stop myself there and say, as an astronomer, when I say metals, I mean anything heavier than helium. So metals are formed in stars or in supernova explosion, both of which happen in the galactic disk. And yet somehow we find lots of metals, actually, well, we find like 75% of all metals to be way out past, outside of the galactic disk. We observe a really rich multiphase gas structure in the CGM. So we have gas clouds that span several orders of magnitude in temperature and density. And by looking at their kinematics, it looks like these cool gas clouds are embedded in warm gas clouds. And when I say cool, I mean something like 10,000 degrees Kelvin, and warm is about a few 100,000 degrees Kelvin. And compared to hot, which would be about 1,000,000 degrees Kelvin. And finally, we observe these huge reservoirs of cool 10,000 degree Kelvin gas that appear to be completely out of thermal equilibrium with the hot halo. So their density is about 2 orders of magnitude lower than what you would expect from gas clouds that were in equilibrium with the hot residual gas in that halo. And understanding how all these pieces fit together is really important to understanding galaxy evolution in general, because galaxies need to form stars in order to survive, and galaxies don't have enough gas within the galactic disk to keep forming stars, but we know that they do keep forming stars. So all of that gas must come either from the CGM, or at the very least, it comes to the galaxy through the CGM. And so understanding that mechanism is really important. And so simulations so far have been really good at reproducing galactic disk structure. So these are all examples of lots of different types of simulated galaxies, over a large number of different masses. And the bread and butter of reproducing the galactic disk structure is thermal supernova feedback. In galaxy simulations, when you have a supernova, you inject heat into the simulation, and the field overall has calibrated it pretty well to reproduce the galaxy. But as it turns out, we're not so good at reproducing the simulated, or the CGM structure at all. So, or with thermal supernova feedback. So for one, it's really difficult to drive strong galactic outflows with thermal supernova feedback, especially for galaxies that are more massive, like our Milky Way. And those galaxies that do manage to drive outflows, or the simulations that manage to drive outflows and have cool gas in the CGM, really struggle to reproduce the observed low densities of the CGM, which imply that there's some sort of non-thermal pressure support that we've been missing. And it's very likely that that non-thermal pressure support comes in the form of cosmic rays. So cosmic rays are charged particles, mainly protons, that have been accelerated to relativistic velocities in extreme shocks, like supernovae. And even though they're moving at relativistic speeds, they stick around in the galaxy for tens of millions of years because their motion is constrained to motion around magnetic field lines, because they're charged particles. And so while they're in the galaxy, they provide pressure support to the thermal gas, which can drive outflows and support this low density gas. And so indeed, recent simulations with cosmic ray feedback have been much more successful at reproducing these observed ionization structures in the CGM. So this is a simulation from Greg Bryan's group. And here the blue dots are the simulated galaxies. The scatter points are observations. And this is column densities, so line of sight densities of cool gas and warm gas. And so here we have a simulation without cosmic rays with just thermal supernova feedback. And here are two different models with cosmic ray feedback, but with different diffusion coefficients. And so you might be tempted to say, well, haven't we solved the problem? Why am I even up here talking about this? But the problem is that we really don't understand, or we don't have cosmic ray transport constrained very well at all. So these simulations don't have predictive power. So for one, we don't really know what fraction of supernova energy goes into cosmic rays. We don't really know how to model, or we don't know how quickly to model cosmic ray transport relative to the gas. So that comes in either through the diffusion coefficient or a streaming velocity. And most alarmingly, we don't know, or there's no consensus in the field as to which transport approximation to use. And traditionally, the two kind of go into either streaming or diffusion. And so groups will pick one or the other, run their simulations, show the results. But what I'm going to focus on is showing that it really matters which approximation you use, and they should give pretty different results for the structure of the CGM. So moving on to the methods, because we can't resolve individual protons and galaxy simulations, we model cosmic rays as a second fluid in addition to the regular thermal fluid. And that fluid moves with the gas through advection, and it can move relative to the gas through either streaming or diffusion. And both of these are approximations of the bulk motion of the pitch angle scattering of the cosmic rays when they're moving around magnetic field lines, when the magnetic field line has a variation that's on the order of the size of the gyro radius of the cosmic ray, so that it scatters them really efficiently. And the two different transport approximations come from whether or not the variation of the magnetic field is driven by the cosmic rays themselves, which would lead to streaming, or if that variation in the magnetic field is driven by turbulence in the thermal gas around it. And so just intuitively, if you had like an initial kind of Gaussian overdensity of cosmic ray energy and a magnetic field line that went in the diagonal direction in this box, the two approximations would evolve like this over time. So they're both moving down their energy gradient along the magnetic field lines, but the streaming case also takes into account the strength of the magnetic field, or the Alfvén velocity, and the direction of the magnetic field. And in the streaming case, there's one more term that comes in that converts cosmic ray pressure into heating the thermal gas, which ends up giving pretty different results for the impact of cosmic ray pressure. And so to kind of highlight the differences between these two models, I made a suite of isolated disk galaxies, so essentially a galaxy in a box. And they're all share the same initial conditions that would produce a Milky Way type galaxy, and they only differ from each other in their cosmic ray transport approximation. And today I'm going to talk about two of those galaxies that really highlight that difference, but there are more that I've run. If you're interested, you can come talk to me about that. And so I used the simulation code ENSO. So during my year as a graduate fellow, I worked on adding the relevant cosmic ray physics to that code, and this past year I've been doing some science with it. And to analyze, I primarily used YT to make most of the plots, and Trident to do basically everything with synthetic spectra, and I'm getting ionization states from the galaxy simulations. So here is where Blue Waters really comes into play, because simulating a galaxy involves lots of different, a wide range of scales. So we're looking at the CGM, which spans hundreds of kiloparsecs. And in order to put that in an appropriate context, the galaxy box is a megaparsec. The galaxy itself is about 30 kiloparsecs across, but the physics that is driving the outflows with individual stars is on sub-parsec scales, which we don't quite resolve. But not only, so even with AMR, this is still a difficult problem to capture. And not only are there lots of grid cells to capture that resolution, all of the cells follow complex physics interactions. So we have the thermal gas, we have magnetic fields, cosmic rays, gas cooling, star formation, and so it can get expensive. And so Blue Waters is really great for this. It helps get the jobs running quickly. They're parallelized efficiently. I have plenty of storage to store my data. And there's a really awesome support team that answers all my questions right away and makes my life really easy. All right, so the fun part is some of the results. So here is an edge-on view of two of the galaxy models. So the columns are the galaxy models. One on the left is diffusion, on the right is the streaming model. The top row is the projected temperature, or density weighted projected temperature, and the bottom row is a slice of that temperature. So it really kind of gives the exaggerated view of what's happening. And so you'll see as the galaxy is evolving, what really jumps out is that in the diffusion model, you have much cooler temperatures and a much more spatially uniform temperature distribution. Whereas in the streaming model, you have this patchy distribution of temperature, which is much more like what we expect to see from observations. And we really don't see this. So in the diffusion model, you have this really large reservoir of cool gas that's concentrated right near the galaxy center and decreases with radius, whereas in the streaming model, you still have, this cool part is the galaxy itself, but everything outside it is relatively warm again. And so one interesting application of this is using these models to understand the origins of oxygen-6 and the CGM. So oxygen-6 is a huge puzzle in the CGM community right now. It's observed in all or nearly all sightlines in galaxies that are forming stars, and basically all radii away from the galaxy within the CGM. And if it's tracing gas that's collisionally ionized, then it traces gas that is supposed to be cooling very rapidly, so you wouldn't expect to see much of it. And because we see it in such abundance, it implies that there's some sort of source or energetic source that's continuously heating up this gas, so that it's constantly cooling and it's caught in the cooling and heating cycle, which is why we see so much of it. Alternatively, if it's photoionized, then we would that it would trace gas that's really, really low density, and it would be out of pressure equilibrium with the hot gas, which poses its own problems. And so here in the top panel, we see the predictions from the two models of the line of sight oxygen-6 column density. And so like the temperature in the diffusion model, you have a really strong oxygen-6 presence right near the center of the galaxy, and then it decreases with radius. Whereas in the streaming, you still reach similarly high values of oxygen-6 in some points, but it's a much more patchy distribution. And because in simulations we have access to the detailed phase structure of the data, we can look at this in a little bit more detail. And so this is the temperature as a function of density of the gas in the CGM, and it's colored by the oxygen-6 mass probability. So the dark points show where the oxygen-6 is most likely to be found. And in the anisotropic diffusion model, we see that most of the oxygen-6 is in this lower left corner, which is low temperature, low density gas that's predominantly photoionized. But in the streaming model, we have, we still have that photoionized oxygen-6, but there's also a significant amount of it that's collisionally ionized, which is the preferred explanation in the literature right now. So this difference between the two models predominantly comes from the distribution, or the differences in the distribution of the cosmic ray pressure in the CGM. So in the anisotropic diffusion model, we see, one step back. So this is the ratio of cosmic ray pressure to thermal pressure as a function of the spherical radius in the galaxy. And the color of the pixels is the density of the gas. So in the diffusion model, cosmic ray pressure dominates near the center of the galaxy and at high gas densities, which is kind of what we saw with the temperature and oxygen 6 distribution. Whereas in the streaming model, the cosmic ray pressure dominates at larger radii and at lower gas densities. And this is kind of a fundamental difference between the two transport models that isn't something that can just be reconciled by changing runtime parameters of one model or the other. And so, in summary, cosmic rays are an important future step for galaxy simulations because we observe cosmic ray pressure to be roughly in equilibrium with magnetic and kinetic and turbulent pressures in the galaxy disk, so we know they're there. And from simulations, we know that they can give pretty, or they can be pretty dynamically important in galaxy simulations, and they can reproduce the structure of the CGM. But if we want these simulations to have predictive power, we really need to think about constraining our models of cosmic ray transport. And so if I had to pick between one over the other, I would say streaming is the better approximation. I didn't have time to show these plots, but it's also a more robust approximation, so it is less, or it relies less on fiddling runtime parameters. But realistically, both approximations are happening in the galaxy, and there's a need to find ways to model both self-consistently. And there have been some very recent works that kind of propose new transport approximations that I plan on implementing in the near future and using that to study the CGM. Awesome. So, thank you.